Yes, the prime numbers, as you know, from most probably you remember from your high school education too, the prime numbers are very important concept based on the divisibility. As you remember that we have started with the modular arithmetics, and it always focuses on the uh, remainders. So here, the prime numbers has no any common divisor, as you know, and a prime number is an integer is greater than one, and that is the divisible by no positive integers and other than one and itself, as you remember from this one. And thousands of years ago, it was known that there are infinitely many prime numbers or many primes. The proof of this fact is found in the works of the Euclid. So, as we have said that the only positive factors of a prime numbers are 1 and itself, just that's it. So the fundamental of the theorem of the arithmetics, the every integer greater than 1 can be written uniquely as a prime or as a product of the two or more primes, where the prime factors are written in order of non-decreasing size. For example, if we want to say that what are the prime factorization, the prime factorization of, for example, 100. How we do this one? 100 has, we can divide it by 2, it will be 50. Divided by 2, it will be 25. And it cannot be divided by 3, it is the next prime number. And then we just search for the next prime number, which is a 5. So 5 can divide the 25. So it will be 5, and another 5, it will be 1. So these 4 of them, 2 multiply 5 and multiply 5, it equals 100, which is the prime factorization of 100, it means. For example, if we call it as 999, for example, at first we are going to check for the first one. What is the first prime number, which is the least one, is 2. But 2 cannot divide at 999. So we are going to start with the 3, which is the next prime number. And it will be 3, 3, 3, and another 3, sorry. It will be 1, 1, and 1. So this 111, it can be divided by 3, 2. If we divide by 3, it will be 37. And 37 itself is a prime number. So the next prime number should be 37. So 3 multiply 3 multiply 3 and multiply 37. These are the prime factorization of 999. So it is, I guess it is very easy, and also it is kind of a reminder for you. So we have a theorem: if n is a positive composite integer, then n has a prime divisor less than or equal to root of n, which means that, for example, if there's 100, and if we take the root of 100, it will be 10. It means that any prime factorization or any prime factors cannot increase, let me say, the prime factors of 100. For example, as we have just seen that it is 2 multiply 2 multiply 5 and multiply 5. As you see, any of them, let me say these prime factors, that they are x1, x2, x3, x4, and it goes on. Any of x or all x's will be smaller than 10 or equal to 10. Okay, this is just a theorem which is produced by some mathematicians. So we have, from the theorem, it follows that an integer is prime if it is not divisible by any prime less than or equal to its square root. So we have to use trial division. We divide n by n, all primes not exceeding this one. And also it is also related with this one too. If we just try to find the factorization of 101, so what it will be, the prime numbers, prime factors cannot be greater or will be less than 10. Why? Because 100 is equal to 10, so the prime factors of 100 or 101 cannot be greater than 10. So for example, 101, actually it is also a prime number. For example, if we try to find 7007, what it should be. For example, at first we have to find if it divides by 2 or not. No, it cannot be divided by 2. And 3, we just check it cannot be divided by 3, and it cannot be divided by 5 too. And the first one is 7. So for 7, it will be 1001. And 1001 can be divided by 7 too. And it will be 143. And 143 is also a prime number. And factorization of this one, as you see, it cannot be greater than square root of 7007. So the prime factorizations of 7007, it will be 7 and 7 and 143. So of course in history there are so many people who tries to find all prime numbers. All prime numbers are very important. Actually, we are going to see where we use the prime numbers, especially for the cryptography. We are make it as secure, especially in the cyber security. So we use these prime numbers. That's why the prime numbers are very important for us. And one of the mathematicians, or one of the interested person, which is the Eratosthenes, he tries to find a way to define the prime numbers, and he takes 100 numbers, and he just start to use, let me say, a way, or just try to find a way to determine what are the prime numbers in 100 choice set. For example, at first we just eliminate 1 because it cannot be a prime number. So he just find the next one, which is the 2, and also 2, if it is the 2, he just eliminates all numbers who can be divided by 2. He eliminates who or which one divided by 2. And now the other ones cannot be divided by 2. So he just jumped to another one, which is 3. And now he tries to just eliminate all of them who are, or which one can be divided by 3. And it is 9 here, 15 here, 21, 27, 33, 39, 35. Yes, great. And I guess that's it. So and then he just jumped to another one, which is the next one, which is 5. And now he tries to eliminate the 5s, change the color. Which one are the 25s, 35, 55, 65, 85, and 95? The other ones are already just done it by the 2. And also, and he jumped to the other one, which is the 7, and we are going to check which one can be divided by the 7. So for the 7 one, we are going to check which one we can just eliminate. This one I just checked. And this one, yes. And this one, I guess. So, and then he just jumped to other ones, which is 11. I think there is no. It's 11. I didn't see, but if you see that, you can do it. But there is no, I guess. And then he jumped to 13. And it continues with the other ones. It doesn't matter. You can just finish this one. And in the end, he just realized that there are some numbers that are prime numbers that cannot be divided by any prime numbers. This is one of the way. So one of the other approach to define any numbers as a prime, the Merson primes just appeared because there are infinitely many primes. Given any positive integer, there are prime numbers or primes greater than this integer. And for almost all the last 300 years, the largest prime known has been an integer of this special form, which is the 2 power of p minus 1. And of course, this p should be a prime number. In this, according to this approach, for example, if the prime number is, let's say it is 3, 2 power of 3 minus 1, it will be this 7. So it works. For example, p equals, let's say, 5. So it is 5, 2 power of 5 minus 1, it will be 31, which is prime number 2. Also, this one is also prime number 2. And according to the Merson primes, it works for very well, but we have some difficulties or some exceptions. For example, here, the numbers 2 power of 2 is prime number, and 3 is prime number, and 5 is prime number, and 7 is prime number 2. So according to these results, we got 3, 7, 31, and 127, which are all the prime numbers. But in this case here, 2 power of 11 and minus 1, it is 2047. But this is not prime number. And that's why this approach has a limitation or has a constraint, which is the prime factorization of the 2047 is 23 multiply and 8 is 89. So here it means that we cannot define the prime numbers very easily or just one approach. In order to actually, because of the development in technologies, the Merson prime noun is now it is here, which is found in 2008. Because of the technology, we can just calculate this prime number 2, and it has 30 million decimal digits inside of this number. So we are going to find the greatest common divisor and the least common multiplies. And also, you just remember from your high school too, most probably, but I'm going to just go fast and that place. Süper Abdülkadir. Bunu arkadaşlarınızla bakabilirsiniz. Thank you, Abdülkadir. And what is the greatest common divisor of 24 and 36? It is actually very obvious to see, which is 12. Why? Because as you remember from here, they, as you see, the common divisors are here, and if you multiply this 3, it will be 12. So this is the common divisor. And what is the greatest common divisor? This one. Actually, we don't have any common divisor, which is only just one, but one is cannot be think or cannot be considered as the divisor, because there is also 17 is a prime number. That's why they do not have any common divisor too. So here we are going to start with the Euclidean algorithm. This algorithm generally used by actually used for finding the greatest common divisor of the two integers. The greatest common divisor, I am going to use that abbreviation. And here it's as a procedure, this is a pseudocode of this one. And now what or how we are going to do is one. At first, this is important. If you try to find a common divisor between the two numbers, always we are going to take the biggest one. The biggest one, which is 287. And there is the approach I'm going to write. At first step, it will be 287. And we are going to find what is the common divisor between this, greatest common divisor between these two numbers. And we are going to check how many times or how many 91 we have inside of the 287. For example, if I multiply, I'm going to open my calculator too. For example, if I do it 91 multiplied by 3, it will be 273. So if I multiply by 3 and plus, it will be 14, right? Yes. So it will be 14. So it means that if I multiply 3, if I multiply by 91 by 3 and I add 14, I am going to get 287. This is the first one, and then we just try, we are going to use that algorithm, that way, in order to get the results. The next one, we are going to use 91, and how many times we have 14 inside of the 91. Yes, Shadid or Abdul Kadir. How many times we have? Yes, 6 times. 6 times we have 14 inside of 91. And is there any remainder? Yes, the remainder is the 7. And then now, as you see here, we are going to use that approach. That one, which is already given in our question, we use on the left side. And then this one, the remainder, we are going to use at here. And this approach will continue. And let me continue. 14 equals how many times we have 7 inside of the 14, which is 2, and plus 0, right? And it is the same as, now this one comes to the left side and the remainder comes to here. So here it's over actually. It means that if there is, this is the last step, this one is the last step. In last step, you just come up with the remainder is 0. Before the last step or previous step from the last step, there is a 7. 7 will be our GCD, the greatest common divisor. We are going to do some more examples with this one, and you are going to just get the idea. For example, find the greatest common divisor of 414 and 662 using the Euclidean algorithm. Okay, at first, we are going to take the biggest one. Biggest one is, or bigger one, you can say, 662 equals how many times I have 414 inside of the 662. If I multiply by 2, it will be greater than the 800. It means that just 1. And plus, what is the remainder? If I just decrease or subtract from the 662, it will be 248, right? So now I'm going to use that one on the left side and that one in the right side. So I continue with the 414 equals how many times I have 248 inside of this one. It is 1, I guess. Yes, and plus if I subtract from the 414, it will be 100. Yes, it will be 166. Now the same, I'm going to use that one at the left side and that one at the right side. 248 equals 166, and it is also 1, and plus, what is the remainder of this one? Just subtract from this one, it's 82, I guess. Yes, Abdulkader, thank you. Thank you, guys. And now the same process I am going to apply. I'm going to use at the left side and this one to the right side. Which one? 66. And how many times I have 82 inside of this one? This 2, right? And plus 2, I guess. And now we can see that 82 equals how many times it has 2 inside of this one. It's 41 plus 0. This is our last step. And we are going to check the previous step of the last step, which is here, which is 2. And this is our greatest common divisor. Okay? I guess you understood the idea. If you have any question, please do not hesitate to find or to ask. Okay, for example, find an inverse of, actually, I'm going to do this one sometimes later, not here, but I'm going to do this one too. So express the GCD. GCD means the greatest common divisor of 252 and 198. So we are going to do the same procedure, but please do remember that it doesn't matter the order of these two, okay? We are always start with the greatest one, the greater one, which is 252 equals 198. How many times we have 198 here? Is 1. And plus, what is the remainder here? Yes, thank you, Oğuz and Abdulkadir. It's 40, 54. And now, continue with the 198 equals 54. How many times I have 54 inside of this one? 3. And plus, what is the remainder? Is 36. Great. So this 54 equals 36. How many times I have 36 inside of this one? Is 1. What is the remainder here? It's 18, I guess, right? Yes. So it is 36, and we have 2 times of 18 plus 0. So in our solution, we can say that it's 18. Of course, it is already given. It is here. But now we are going to use substituting the expression for the 54 into the previous equation. So I'm going to show you how we can find the linear combination of this one as well. Also, we use a Euclidean algorithm, but I'm going to show you another part, another type of this one. So here we can say that at first we can say here what is and here and here. At first we are going to see the linear combination. The linear combination, it means x and y pairs here. In this case, you are going to use, and we are going to start not the last one, but the previous step here. 18 equals, we can say 1 times 54 and minus 1 times 36. Do not try to multiply. For example, in this case, do not multiply and write the result of the 3 multiply 54. Okay, do not, just use that. We have 354. Here, for example, we have 36, or here we have 198. Do not multiply. For example, if it is 2 here, we do not use, or we shouldn't multiply this one. We just think that we have 3 times 54, or we have 36 2 times. Okay, do not multiply them. For the other step, we can say that 36 equals 198. We have just 1, and minus 3 times 54. And also we have 54 equals 1 times 252 and minus 1 times 100. 1 times 198. In this case, if we try to find the linear combination of these two, it means we have to find the coefficients of these 2 digits, or these 2 integers. So this is the previous step. These are 2. Now we are going to check if the remainder is the same. I'm going to write here. I'm going to change the color. So it is 18 equals 1 times 54 and minus 1 times 36. But 36 here and 36 here, I am going to rewrite at that part as 36, which is 1 times 198 and minus 3 times 54. Okay? Is that understood? Now I continue with here 18 equals 1 times 54 and minus 1 times 198 and plus 3 times 54. And 3 times 54 here, 4 times 54 here. So it will be 4 times 54 and minus 1 times 98. It equals 18. Now I'm going to change the color again. Now I have 54, and also I have a 54 information here, and I'm going to use that 54 inside of this 54. So I'm going to rewrite here 18 equals 4 times 54 and minus 1 times 198. So I'm going to rewrite as 18 equals 4 times, what is the 54 is 1 times 252 and minus 1 times 198 and minus here 1 times 198. So here we can say 18 equals 4 times 252 and minus 4 times 198 and minus 1 times 198. it means that 18 equals 4 times 252 and minus 5 times 198. So here the linear combination, of the GCD 252 and 198, it doesn't matter the order of these two, equals 18. It means that this one is y and this one is x. X equals minus 5 and y equals 4. This is, or you can say that 18 equals 4 times 252 and minus 5 times 198. And this is our x, and here it is y. We are going to do some exercise with this question or with this subject, so do not worry about it. So here it is the same process we are going to continue, or we are going to apply. So the biggest one is 270 and the smaller one is 192. So it is the same procedure we are going to follow. It doesn't matter what is the remainder or what is the greatest common divisor. We are going to find actually. So in this case, 270 equals, how many times we have? 1 times, of course, and plus 78. I guess Charlotte did the calculation. So here we are going to use 192 equals, how many times I have 78 inside of this 2, and 192. I guess it's 2 and plus the remainder is 36, right? The remainder is 36. And now we have 78 equals, how many times I have 36 inside of this one is 2 plus, yes, it is 6, and 36 equals 6. How many times I have 6? 6 times, and plus 0. So here the greatest common divisor here, this is our greatest common divisor of these two integers. And let me show you again here, as we know, we use that one on the left side and use that one on the right side, and also, and then in the other step, the next step, we use 78 to the left side and 36 to the right side, and then we use 36 on the left side and 6 on the right side. Okay, just to be clear again. So here, what we are going to do, as we did before, we are trying to just keep the remainder on the left side. Yes. So at first, we just keep it to the left side, and it equals 1 times we have 78. It comes from here, and minus 2 times 36. And this one, the remainder of this one is 36, which is our remainder. And 1 times 192 we have, and minus 2 times 78. And here it is 78 is our remainder, and 78 equals 1 times 270 and minus 1 times 192. Always we start, by the way, this is 0, not 6. So we always start from the previous step or the last step. So here we have this explanation. I continue from here. So I have 6 multiplied by 6 equals 1 times 78, because the next step I am going to use 36. I'm going to use 36. That's why I will rewrite these expression inside of this one, or substitute, let me say. So minus 2 times, what is the 36? 1 times 192, and minus 2 times 78. Now it is 6 equals 1 times 78 minus 2 times 192 and plus 4 times 78. 4 times 78 and 1 is here is 5 times 78 and minus 2 times 192. It equals to 6. Now I'm going to continue from here. So now we have 87, and also we know what 87 is. So we are going to rewrite that expression inside of this 87 here in our last equation. So it is 6 equals 5 times 1 times 270 and minus 1 times 192 and minus 2 times 192. So 6 equals 5 times I have 270 and minus 5 times 192 and minus 2 1 times 192. So in this case, in the last step, 5 times 270 and minus 7 times 192. So in this case, we can say that the linear combination, change the color, the linear combination of 270 and 192, it is 6 equals 5 times 270 and minus 7 times 192. And in this case, this one is our y, and the minus, this is x equals minus 7 and y equals 5. Okay, we can continue with this one, and also these are for practice for you. I think you just got the idea. That's why no need to solve and no need to just take our time to hear. It is the same. Use the Euclidean algorithm to express greatest common divisor. It is very easy. Actually, you can do it just in a minute, I guess, because we are going to take the 191 equals 26. How many times 26 we have inside of this 91? Yes, Abdulkadir, it is 3. And minus plus. Yes, 13. Thank you. And then we have 26. How many times we have 13 inside of this one? This is just 2 and plus 1. This is our last step. So it means that the 13 equals 1 times 91 minus 3 times 26. So this is our linear combination of the 26 and 91. And also, this is, what is this one? This is the last step, and this is the previous step of the last step. It means that this is our greatest common divisor, which is 13. Okay, the inverses, we are going to find the inverses. What are the inverses is, or solving the congruences? We are going to find the inverses of any integer in some definite or determined modular arithmetics. For example, here actually we have another example too, but I'm going to show you that one too. In this case, the theorem says once we have found an inverse of A in modulo M, we solve the congruences as here by the multiplying both sides of the congruence by this inverse. And also, we can just find that if it is the inverse of a mode, for example here, where M is a positive integer, and A and B are the integers, and X is a variable and is called a linear congruences, and such congruences arise throughout the number theory and its application we use. But here, how we can find the inverse of 17, for example, in modulo 43. In this case, what we are going to do, an expression is given as here, it says, and as a linear combination, find the X by using the Euclidean algorithm. So, in modular arithmetics, or in modulo 43, we are trying to find an X, a variable. If I multiply this variable by the 17, and if the remainder is equals to 1 in modular 43, it means that this is an inverse of 17. Okay? If, for example, there is A multiplied by B, the remainder is 1 in modular C, let me say, it means that A, let me say, the B equals the inverse of A. Okay? Or the B or the A equals inverse of B. Whatever you just want to show. Okay? Now it is the same for here as we just use. Let's change the color. We are going to use a Euclidean algorithm to find the inverse of an integer in specified modulo. For example, here it is, the biggest one is here. Actually, it is modulo equals how many times I have 17 inside of the 43. I guess it is 2, right? Yes. And what is the remainder? Is 9, I guess. Yes, thank you. And now this is the same, and the same procedure we are going to continue. It is 17. It equals how many times we have 9 inside the 17 is 1, right? And plus 8, and this is 9. How many times we have 8 inside of 9 is 1, and plus 1, and equals 8, and we have 8 times 1 plus 0. This is our last step. We are going to check the previous step here. As you see here, it is the remainder is 1, which is our GCD. If GCD equals 1, then we can say that 17 has an inverse in modulo 43. If GCD equals 1, we can say that 17 has an inverse. But if GCD is not equal to, or does not equal to 1, it means that there is no inverse. If it is equals 1, then we can continue our the same procedure that we have just seen. How we just find the linear combination of these two integers. We are going to apply the same procedure for here. But if it is not 1, if the GCD is not 1 here in the previous step, you do not need to do the following procedure. But if it is 1, we have to continue to find. Now I'm going to continue from here. At first, this is 1. 1 equals 1 times 9 and minus 1 times 8. And the next one is 8 equals 1 times and 17 minus 1 times 9. and here it is 9, and 9 equals 1 times 43 and minus 2 times and 17. Now we are going to continue with this one. I'm going to change the color itself. So 1 equals, at first we are going to use or rewrite the 8 because the next step we see the 8. So 1 times 9 minus 1 times 8, inside of the 8 we are going to use that expression, which is 1 times 17 and minus 1 times 9. So 1 equals 1 times 9 and minus 1 times 17 and plus 1 times 9. So 2 times 9 minus 1 times 17 equals 1. Now we are come up with the 9 here, and we are going to rewrite or substitute with this expression with the 9, and 1 equals 2 times 1 times 43 minus 2 times 17 and minus 1 times here 17. So 2 times 43 and minus 4 times 17 and minus 1 times 17 equals 1, and 1 equals 2 times 43 and minus 5 times 17. So here this minus 5 is inverse of 17. So this is minus 5. Minus 5 equals the inverse of 17. But we do not use minus numbers in modular arithmetics. That's why we have to add minus 5 to the modulo itself. It's 43. So it equals 38, right? So the 38, if I multiply 38 by the 17, the remainder will be 1 in modulo 43. Let's check it. For example, here, if I multiply 17 by the 38, it will be 646. And if I just use the modulo 33, the remainder will be 1. The result is, you can say that in the end, as a result, minus 5, not minus 5, 38 is inverse of 17 in modulo 43. Now we are going to go back to find this one too, for example. So here it is the same procedure. We have to continue, or we are going to apply. Let's do it together. The biggest one is modulo itself. You can just write this expression as, there's a 101. This is prime number, we know that. And also there is one number I have to multiply by the 101, and the remainder will be, or should be, 1 in modulo 4620. It is the same expression with this one too. We are going to check if there is an inverse at first, and then we are going to find the inverse of 101. So let's start solution. We have a modulo, which is the biggest one, 4620 equals 101. And now, how many times we have 101 inside of 4620? 45. What is the remainder? it is 75. Great. So the same procedure we are going to apply. It is 101 equals, we have just 1 times 75 and plus we have 26. Great. And 75 equals, how many times we have 26 inside of the 75? It is 2, right? And plus 23. Great. And 26, we have just 1, 23, and plus 3, and 23 equals, how many times we have 3 inside of 23? It is 7, and plus 2, and now it is 2 equals 1 times 2 and plus 1, and now it is 2 equals 2 times 1 and plus 0. This is our last step. Now we are going to continue with the previous one. So at first, let's check the inverse. So this one is equals to GCD. If the GCD of 101 and 4,620 equals 1, so there is an inverse, we can say, right? Yes, it is, the GCD is 1. That's why we can say that they have an inverse. It has an inverse. 101 has an inverse in modulo 4,620. Okay, now we are going to do the same approach or the same implementation, which is 1 equals 1 times 3 and minus 1 times 2. And this one, 2 equals 1 times 23 and minus 7 times 3. And here we have 3 equals 1 times 26 and minus 1 times 23. And this one equals 23 equals 1 times 75 and minus 2 times 26. And here we have 26 equals 1 times 101 and minus 1 times 75. And here we have 75 equals 1 times 4,620 minus 45 times 101. As you see, it is very easy. Actually, it's a bit time consuming, I know, but the same procedure you are going to apply. This is very easy to implement, but you shouldn't do any mathematical mistakes. So, of course, all of us are human, so we made some mistake we may make. So here we are going to continue to our approach to implement to solve this question. So here we are going to start with this one. As now, the next one is 2. It means that I am going to rewrite the 2 here. So I continue with here. 1 equals 1 times 3 and minus 1 times, inside of the 2, I'm going to write this expression, which is 1 times 23 and minus 7 times and 3. So 1 times 3 minus 1 times 23 and plus 7 times 3, and it means that 1 equals 1 times, equals 8 times 3 and minus 1 times 23. So here the next one is 3, and I'm going to rewrite the 3 inside of here as that expression, which is 1 equals 8 times 1 times 26 and minus 1 times 23 and minus 1 times 23. And here is 8 times 26 minus 8 times 23 and minus 1 times 23. And now it is 8 times 26 and minus 9 times 23. The next one is 23. I'm going to substitute with this expression, which is here actually. So 1 equals 8 times 26 minus 9 times, what is the 23 is 1 times 75 and minus 2 times 26. So here 1 equals 8 times 26 minus 1 times 75 and plus 18 times 26. So 18 is here, 8 is here, 1 equals 26 times 26. I'm not going to multiply it. I also do not think that this is the 26 square, okay? You just have 26 times 26. That's it. And minus 9 times 75. At the next step, we are going to use 26 here. And it is 1 equals 26 times, what is the 26? Is 1 times 101 minus 1 times 75 and minus 9 times 75. And now it is 1 equals 26 times 101 minus 26 times 75 and minus 975. So it is, yes, 1 equals 26 times 101 minus 35 times 75. We are going to rewrite the here with this 75, but I'm going to write this one as here. And I'm going to change the color. Actually, not. Yeah, let's. No, not. I'm not changing the color because of the perception of your solution of your view. So here is 1 times 1 equals 26 times 101 minus 35 times 75. What is the 75? Is 1 multiply or 1 times 4620 and minus 35 times 101. Okay, this one is better. Okay, so 26 times 101 and minus 35 times 4620 and plus, what is the multiplication of the 35 and 45 is 1575. Thank you, Sharit. Yes, 75 times 101. So here 1 equals, and in the last step 26 we have here, and we have 1575 is here. We are going to add to each other. It means that we have 1601 times 101 and minus 35 times 4620. So in this case, what is the inverse of 101 in modulo 4620, which is the coefficient of 101, which is 1601 is inverse of 101 in modulo 4620. This is our result. It is minus 35 multiply 4620. It is not a minus. Shut it. And 35 is linear combination of as you remember this one, just a couple minutes ago, we have seen the 35, the minus 35, it is y. Actually, we have to add 4,620 in order to get the positive integer. And also the x equals 1,601, which is our x. Yes, mode is not 101. The mode is 4,620. This is our mode, the modulo. Here is the integer. We are going to find, we try to find the inverse of 101 in modulo 4,620. This is the x. It means that if I multiply, let us do it if you wish. If I multiply 101 by 1,601, the result is 161,701. If I divide it by the modulo 4,620, I try to find the remainder. The remainder is 1, as it is already. Yes, if you take the modulo of this number, 161,701, if you just try to find the remainder by the, or in modulo 4,620, you see that the remainder will be 1. So you know how to use the calculator. So in the final exam, of course, you are going to use your calculator. Do not worry about it. Okay, now we are going to continue with our other example. Not this one. Yeah, this one is actually was easy one. Now, what are the solutions of the linear congruence, which is 3x? If I multiply by 3 by the one of the integer, and the remainder will be 4. What might be the x is? So in this case, we can say that if you do the mathematics as 3x equals 4 in modulo 7, if I multiply by minus 2 for the both sides, it means that it will be minus 6 multiplied x equals minus 8. So the minus 6 actually in modulo 7, it is 1. So x will be, it is in modulo 7, the minus 8 if you divide by the 7. So we are trying to find the closest but smallest one, which is minus 2 minus 14. If I subtract it, it will be plus, or it will be positive, and the x will be 4. In fact, if I just multiply by x, it will be, if x is 6, it will be 18. If you divide by 18 by the 7, it will be, the remainder will be 4, which is here. So this is just some mathematics, but we always use the modular arithmetic as a block, and you should always try to find the remainder. We always try to find or try to focus on the remainders. So the other one is the Chinese remainder theorem. And the Chinese remainder theorem is a bit similar with the Euclidean algorithm. That's why I'm going to explain this one for the next week. But we are going to move a bit fast from the next week. Okay, do you have any question till now for the Euclidean algorithm? Actually, if you do some practices, it will not take so long, I guess. But before the exam or before the uh, actually yes, before the exam, you should do some practices, and also you can do practices in any time. But if you do practices, you see that it is not very complicated actually. But you should focus on the question itself. If you just if your attention or if your focus is distracted, you cannot find the way, so you may start from all over the question. So that's why it is very important to be focused on the question and the solution, and do not try to, or just avoid yourself to be distracted while you are solving the problems. Especially in final exam, do not try to look at your phones or your friend's paper, because you may just mix them all up. Yes, of course you can. You can find the GCD. Yeah, yes, the greatest common divisor, but you cannot find the linear congruences by the method we use in primary school or high school. Yeah, in order to find the inverse, for example, you have to use the Euclidean algorithm. Okay, guys, that's it for that this week. Yes, if you like the video or the course, please press the like button here. Okay, have a nice day and have a nice